would be this B, right? So this is the impact parameter for a particular trajectory. So you can see that just go from top to bottom, you can see how the trajectory bend, right? So for this one, when the particle comes in, right? So and it go out, it still pretty much go horizontal, right? So and as you just go down to consider other trajectories, as you decrease the impact parameter, you can see that the bending of the trajectory getting more and more significant, right? So if you look at this one, right, so it bend a little bit more. If you, for example, look at this one, it goes like this, right? So and if you look at this one, it bends even up. So the bending, right? So as you decrease the impact parameter, it's more and more significant, and that makes sense, right? So because as you have closer and closer, small and small impact parameter, that means that you are closer and closer to your scattering center, right? So and that you feel stronger and stronger repulsion. Okay. Okay. So here, let me again just label the scattering angle, right? So for example, for this trajectory, right? So the scattering angle would be this one, right? So for example, for this trajectory over here, right? So the scattering angle is about this one, right? And so on. You can draw the scattering angle for each trajectory. Okay, so here you can see a graph that I plot over is that for each trajectory, right? So I label the impact parameters. Okay, so from near to far, right? So this one is pretty much this one, right? So and this one is more like this one. And then for each of them, you have different scattering angle, right? You can see that, as I said already, right? So if you have a very, very small impact parameter, small b value, so then the scattering angle would be very large, right? So and as you go up, then the scattering angle getting smaller and smaller. So you could imagine that if you really, the impact parameter is getting like tends to infinity, right? So you should have zero scattering angle, right? Because essentially there's no interaction between your incoming particle and the scattering center. So that won't be, essentially that won't be scattered at all in the sense. So in fact, okay, so this one, so let me kind of draw an interpolation for all these points. Okay. So the function that representing this curve, okay, we will actually derive that a bit later. Okay. But anyway, right, so this picture really are from actual calculations for the Rutherford scattering. So now I want to ask the following question is that if I want to go, if I want to have a particular range of scattering angle, so then what range of impact parameter am I allowed to have? Okay, so that is to say, for example, an example is that if I suppose the detector that I have will cover some angular range, right? So it has to be very small, but just for illustration purpose, I'll just make it a bit bigger. Suppose I want to look for the particles that is scattered into the angular range between 35 and 40 degrees. Okay. So if I want that, what is the range of impact parameter that I'm allowed to take? Right. So that is not difficult from this plot. Right. So you just need to kind of take this point and draw the vertical line down to the x-axis. Right. So and this one also down to the x-axis. Right. So that is if I want to go within this delta phi prime, then the range of the impact parameter I'm allowed to have is over here. Right, is this range over here. This would be my delta B. Okay, so then I can have a ratio delta B divided by delta phi prime, which give me some number anyway. Okay. So now I ask another question. So what if I want to have consider that the particle that goes within 10 to 15 degree. So like over here. So this is another detector. Okay, so that helped me to detect any particles that go within the range of scattering angle from 10 to 15 degrees over here. Right, so another delta phi prime over here. So then again, I ask the same question. Then what is the range of impact parameters that I'm allowed to have? Then from this plot, you can see that over here, this time I'm allowed to take a rather wide range of impact parameter, right, in order to fall into this range. Okay. So you can see that this delta B, right, so corresponding to this different delta phi prime, okay, so will be different. Okay, so if you want to have a large scattering angle, in this case, the delta B is quite restrictive, right? So you really need to fall within this narrow range. Okay. So on the other hand, if you want to go to kind of the small scattering angle range, okay, so it's much less restrictive. Okay, so you have a wider range of impact parameter that you can choose. Okay. So this is the quantity that is closely related to this differential scattering cross-section that we'll be talking about. Okay, is this ratio. Okay, so bigger value for this, that means it's easier to go into that range of angle, right? So and vice versa. So the scattering cross-section that was defined is well, it's not exactly this delta B delta phi prime, but I'll show you that would be exactly related. But the scattering differential scattering cross-section is this D sigma. Okay, so divided by this D omega. Okay, so you could imagine why this D sigma is closely related to this dB, right? This delta B, right? So because this D sigma over here is this area. Okay. So and as I explained already, what is D omega last time? Also, that would be the solid angle of one of the detector, and that also, right, so give you some range of scattering angle over here. So now let's try to derive a mathematical formula for this D sigma D omega. Okay. Okay, so we are considering a problem with central force, and of course it's natural to use the spherical coordinates, right? So because as I said last time, right, so the detectors that I'm putting on is consider a virtual spherical surface like this, right? So a virtual spherical surface like this. This sphere has to be very, very big, and then the detectors, right? So they will cover every part of your spherical surface. Okay. So before looking at this picture, so let's go here. So this is, if you still remember, this is the differential volume element, right? So for a spherical coordinate, right? So and you may still remember how to write down this dV, right? So but this time, what we are interested in is just this part. So this part is this surface of this differential volume element, right? So, and this part has an area dA, right? So this part has an area dA, which is given by r squared sine theta d theta d phi. Okay. So one thing you need to be careful is that, but I'll explain a bit later, is that the notation of angle over here is slightly different from what we'll be using here. Okay, but I'll explain that. But first of all, remember that this dA written like this for spherical coordinates, right? And of course, then I really want, actually what I want is a solid angle, right? So not really the dA, so I want d omega. So then, right, so this d omega is given by dA divided by r squared, right? So then that would be sine theta d phi. Okay, so now I want you to look at this sphere. Okay, so how do we fit in this spherical coordinate over here? Okay, so be careful is that in this picture, right, so the z-axis is pointing up. However, in this case, the z-axis is pointing horizontally. Okay, so be careful about that. Now, you can see that this theta is what we call the polar angle, right? So we use theta. Okay, so but here in the scattering problem, okay, so we use this phi prime. Okay, so this theta really means this phi prime over here. Okay, and then there's another angle in the spherical coordinate, which is this phi. Okay, so and that this variable is turns out to be not important for the central force, as I will explain. But let me also draw the phi in this picture, right? So if this is z-axis, so let me call this the x-axis, and this one to be the y-axis. Okay, I see how this is flipped over here. So now, if I'm considering, right, so a particular surface area element over here, right? So then the phi that I'm talking about would be this one. Okay, so then now we have worked out the arrangement for this coordinate system, right? So now as I said, I want to find out this. The goal is to find out this d sigma d omega, right? So here you can see that I have drawn not just one detector now. I have drawn an entire set of detector. Okay, so which lies on a particular circle, right? So on this sphere, right? And also for this S-plane, right? So a virtual plane, right? So for this incoming particle, I have also drawn an entire circle or a ring, okay, a ring area, okay, for the d sigma. Okay, so the fact that I don't need to just consider one-to-one at a time, but I can consider the entire ring at a time is because of the fact that we have symmetry in this problem, right? So that is to say, the problem itself, right, so does not depend on this phi angle, right? So the meaning that if I rotate the whole system like this, right, so by any angle, right, so the entire system is not changed, right, because it's central force problem, right? So that is to say, if I know that the particle which passes through the top element in this ring, then it will reach this top detector over here, right? And similarly, if this detector, if this particle originally passes through one of the elements on the leftmost side over here, then I know that it will also go to the detector of the leftmost side. Okay. So therefore, can really consider the entire thing all in once. No need to consider each one individually. Okay, so now, as I said already, is that this one is the d omega, right? This is my d omega, dA. Okay, so if I am labeling this area, this is the dA, so which is the r square sine phi prime d phi prime d phi. Okay, so see how it is slightly different than this one because I'm using phi prime. This is using theta. Okay, so this is psi phi prime. Okay. So now, if I'm going to ask, what about the entire area of this whole thing? Right. So what do I need to do? Right. So the entire area of this whole thing would be you just need to do an integration, right? So over this phi angle, right? And that would be, so that's what I'm going to do is that if I'm referring to the entire area, so let me just remove that arrow. That would be this, right? And that just gives me a factor of 2 pi, right? So this integral. So just 2 pi sine phi prime d phi prime. Okay. So this is the dA. Okay, so the dA means the area of this entire thing. What about the solid angle corresponding to this entire dA? Right, so that would be, oh, I'm missing a R square over here. Okay. That would be this expression here divided by R square, right? So that's why my d omega is just 2 pi sine phi prime d phi prime. And that, okay, so and I've written down here. Okay, so this is why I have this d omega equals 2 pi sine phi prime d phi prime. Okay. So that's pretty much for this d omega. So, and what about this d sigma? Right, so I want to find the ratio between this sigma and this d omega. So d sigma, if you look at this picture here, you could immediately conclude that, right? So this ring area is just given by 2 pi b db, right? So because the radius of this ring area is b. Okay. So then what's next is that I just need to divide this one by this one, was d sigma divided by d omega. So, and it's just written down over here. So d sigma d omega, right? Just taking the ratio between these two expressions here. And over here, you can see that I have this db d phi prime. Okay. So now, remember this db d phi prime. I gave you an example here already. So this is the db d phi prime. Okay. So that is to say that this is the ratio, right? So between this range of the scattering angle and the range of the impact parameter that you are allowed to take. So, and here I just cancel out the factor of 2 pi, and also you see that I put an absolute sign for this db d phi prime. Okay, so this is just because by definition, okay, so this differential scattering cross section is an absolute value. Okay, so that's why I put an absolute value for this db d phi prime. Okay, so from this example already, you can see that if you just take the because this dB phi prime is the inverse of the slope of this curve, right? So in this case, you clearly see that the slope is negative. So in this case, dB phi prime is negative, right? So, but at the end, we don't care about the sign, but we just take the absolute for this, okay? So then this is a formula that we'll use, right? So is that you can see how this a quantity here, depending on the relation between the scattering angle phi prime and the impact parameter b. Okay. Then the question remains is that how do we find the relation between the impact parameter b and the scattering angle phi prime, right? And that would depend entirely on the nature of your central force, right? So whether it's a 1/r square, whether it's 1/r cube or other things. So different kind of central force will give you different relation between the B and the scattering angle, the scattering angle phi prime. Okay. Okay. So then, before I move on to actually do the example, so I also need to tell you the definition for the so-called the total scattering cross section. Okay. So total scattering cross section is defined as the surface integral, okay, so of this differential cross section. Okay, so what it really means is that you take this d sigma d omega, right? So for a particular point, right? So and then so different points on this spherical surface, right? So we'll have different value of d sigma d omega, right? So and then at the end you just integrate over the entire solid angle, right? Covering the entire sphere. Well, that would be a 4 pi solid angle, right? So in that one, if you again use the spherical coordinate, it is as written like this. Okay, so this is known as the total scattering cross section. Okay, so and physically, what it represents is the effective area of the force field for producing a scattering event. So what does that mean? So it means that so if I go back to this picture, okay, so I have an example later that will be more clear. But look at this picture again, right? So you're firing a shower of particles over, and then they are all being scattered in the sense that the scattering angle are non-zero, right? So but you could imagine that as you have a larger and larger impact parameter, right? So the scattering angle will approach zero, right? So and for those parts, we will say that no scattering occur. If the scattering angle is zero, that means it's not affected at all. So that means no scattering. Okay. So you could imagine that for the problem, right? So if you just keep increasing your area of your beam, of your particle shower, so then that means that what you are going to do is the following, right? So you're increasing the area of your particle beam will be something like this, right? However, eventually you'll find that if you are the outer area, the particle in the outer area at the end won't be scattered at all, right? So perhaps only the particles within, for example, this range will be scattered, right? And everything outside won't be scattered. And in that case, I will say that the scattering cross-section is the area of this purple circle that I draw. So, but it turns out that for the Rutherford scattering, for the 1/r square, the scattering cross-section is actually infinite. Okay, but there are other cases that will be finite. Okay, but one thing you can also imagine is that if this force is strong, right? So then you could imagine that this scattering total cross section will be big, right? So because if it is strong, that means that even you are kind of far away, you will still be affected. Okay, example will come later, but so let's focus on the 1/4 square problem, right? So because that's the orthodox scattering. Okay, so orthodox scattering, right? So exactly is about the repulsive 1/4 square electrostatic force, right? So and we want to show that in this case, the differential scattering cross section is given by this formula over here. Okay. So of course, this is the final result, but what do we approach? How do we approach it, right? So of course we just use the formula we have just learned is this d sigma d omega is given by this b divided by sine phi prime absolute value of db d phi prime, right? So we are going to work out the relation between this b and phi prime for the Coulomb field. Okay. So actually, I'm just going to apply the result that I mentioned last time. Is that if I have this 1/r square, that is if the potential is 1/r, then my scattering angle is related to the eccentricity of your hyperbola trajectory by this formula. Okay, so this is a formula that I'm going to use. Okay. So that is, let me start from, so if I say that phi prime is equals to 2 arcsine of 1/epsilon, so that means that is equivalent to say that this sine of phi prime divided by 2 is equals to 1 divided by epsilon. Okay. So remember our goal. Our goal is to find out the relation between the phi prime and the impact parameter b. Okay, so that we can do this db d phi prime. Okay, so that means we need to know the relation between the impact parameter and the epsilon of the trajectory. Okay, so remember the epsilon, right? So the epsilon by definition, right? So it's given. It's what we learned already, right? So I just use a definition to the formula that we have learned before already. So this is nothing new. This is just from part 1 of this chapter. So this is what you will get. Okay, so first of all, 1/epsilon is this 1 to the power of -1/2. Okay. So then our goal is to work out how this is related to the impact parameter b. Okay. So that would of course be related because as I told you last time, right? So the initial angular momentum L is given by this linear momentum times the distance. That the distance is the b. Okay. So that's why we can substitute this L square equal to m square v naught square b square into this expression over here. Okay. And this one, so then here is just some manipulation of the symbols. Right. Right, just like this, nothing but just substituting that into it. So, and I can just cancel out the factor m, right? Okay. And then next, I'm just going to just for convenience. Okay, just for convenience, I'm going to define a new symbol. Okay, so is that I'm going to let this b naught to be k divided by 2e. Okay. So just to make things look simple. Okay, so then if I define it this way, you'll find that the expression here can be written as 1 plus b squared divided by b naught squared to the power of minus 1/2. So that means the sine of this is equal to this, right? And now using a trigonometric formula that this, right? So this tangent square something would be equals to the sine square of something divided by 1 minus sine square, right? So using this formula over here, we'll be able to find out that tangent of phi prime divided by 2 is given by this b naught divided by b. So that's great, because now we have found out the relation between this b and the phi prime, right? So and we want to take the derivative, right? So that's where we can start that. Okay. So for this one, we can see that this db d phi prime is given by minus cosecant square times b naught divided by 2. Okay. So okay, I have a minus sign here, but remember, we just need to take the absolute value, right? So this minus sign doesn't matter. Okay. So now if you go ahead and plug in this expression to this part, right? So and then do it, multiply by b divided by phi prime, right? So you get the result of this one. Okay. So if we look at the final result over here, right? So it will depend on k squared. So what is k? Remember what is k? The k is that the Coulomb potential, right? So the Coulomb potential is given by k divided by r, right? So it makes sense that it depends on k, right? So as a larger k, that means a stronger force, right? And a stronger force eventually lead to a larger differential scattering cross section. Okay. And it will also be inversely proportional to the E. What is E? Okay, so E is the energy of the particle, by the way. So the energy of the particle also can be calculated just by the initial kinetic energy, right? Initial kinetic energy. So, and it is inversely proportional to that. And can we make sense of that? Right. So again, just look at this picture over here. So larger E, what does that mean? Larger E, that means that the particle comes in really fast. Right? So if it comes in really fast, it bends less. Right. So that's why that would be inversely proportional to this E squared. Okay. So, and one more remark here is that what about the attractive Coulomb potential, right? So here I'm considering with the thought experiment, right? So it's the alpha particle with the nucleus, so both positive. What if we consider not shooting alpha particle, but shooting electrons to your target, right? So then what will happen, right? So remember last time I said that even for the attractive Coulomb potential, the scattering trajectory is also hyperbola, right? So but if I'm going to draw the picture, right, the hyperbola won't be looking like this, right? So the hyperbola that you'll be expecting should be well, maybe not very good drawing, but should be something like this, right? So, right, bend the other way, so attraction, right? So the hyperbola should not be like this, right? It should be like this, right? Being attracted, and maybe this one looks like this. So this kind of hyperbola, if you have this attractive force. So if I also want to consider the scattering cross-section, all I need to do is that I need to just replace this k by minus k, right? And in that case, you can see that it does nothing because I have the k squared, okay, for the final result, okay, over here. But what about phi prime? Will phi prime change? Okay, right. So if you just go take one step backward, right? So actually look at what we have over here. It also doesn't matter, right? So here I have this b squared and this b naught squared, and again this k is contained in this b naught, right? So but because b naught is square anyway, right? So then I have this minus k, or k doesn't matter. So then that means attractive Coulomb potential or repulsive Coulomb potential, okay, will give you the same differential scattering cross-section anyway. So one last remark here, okay, is that if you are go ahead and use this formula to find the total scattering cross-section, okay, you actually get an infinite result, okay, if you actually do the integral. But as I said, so what does it mean? So that means that what is the total scattering cross-section, as I tell you, right? So is that, imagine that you have this shower of particles and then you keep increasing the area of your shower of particles. Is that how much, okay, area in this shower will experience scattering, right? So as I mentioned, right, so if it's too far away, right, such that it does not be scattered anymore, then those don't count, right? However, it turns out that for pure Coulomb potential, even you are very, very, very far away, you will be scattered a little bit still, because the 1/r will still have some influence on you, okay? However, in practice, we won't be getting infinite result. Okay, why is that? Because when we do this experiment, we were considering the alpha particle in the nucleus. However, we do have electrons outside, right? So because this is the nucleus, but in practice, in the experiment, we do have the electron cloud outside, right? So in this atom, right? So that is, if your impact parameter is so large, right? So it no longer see this pure attractive, pure repulsive Coulomb potential, right? So if you are so far away, if your neutral atom is like this big, if your impact parameter is so far away, then that particle will only experience a neutral atom. And for that one, basically, you don't see any Coulomb repulsion at all. Right. So that is, in other words, right? So as you go to larger and larger impact parameter, right? So effectively, it's really not a pure repulsive Coulomb potential. As you go further and further away, you feel a little bit of cancellation, okay, due to the electron cloud. Okay, but that's one remark about that. Okay, so now let's take a break. Okay, so let's take a 15 minutes break, and then I'll come back to talk about the the last example. Okay, so for this part of the chapter and also for this entire chapter, you can try it yourself during the break if you want. So this is about something much more simple. Okay, so essentially it's a toy model that I am like playing with this elastic collision. Okay, so I have this hard sphere over here. You could just consider this is a small metal sphere. This is a large metal sphere. Okay, so when the particle hits the surface of this sphere, it just bounces off. Okay, like this, and then I'm just considering this is a pure elastic collision. Okay, so such that the relation between the angle of incidence and the angle of reflection, okay, so it's simply given by the like the law of reflection, right? So this angle of incidence is equal to angle of reflection. So that's the rule. Okay, so for this problem here. Okay. Principle, this is still a central force problem, right? So what the particle sees is that no force, no force, no force, no force, and then until it hit the surface of this big sphere, it received an impulse, right? So which is pointing directly away from the center of the sphere. So that's the force. Well, impulse is the force time delta t, right? So try to find the differential cross section of this. We'll come back at the 10:30. Okay. Okay, so let's work on this last example problem. Okay, so and then we'll move on to the next chapter. So, well, differential scattering cross section, right? So again, we are going to use the same formula. Right, so you know that again, the goal is to find out the relation between the impact parameter and the scattering angle. Then we should be able to work this out. Okay. Okay, so in this case, where is the scattering angle? Okay, so the scattering angle is over here. But again, the green one is phi prime. Okay, and this is the impact parameter. So you could imagine that if you have an impact parameter which is larger than the radius of the circle of the sphere itself, then actually that there will not be any scattering, right? So the radius of the circle or of the sphere is a. Okay, it's not very good. Okay, so now it is an elastic collision problem with a hard sphere. So as I told you already, I have this angle of incidence equals to angle of reflection. So then I have this to be alpha. This is also alpha. Okay. So now if I go to use the similar triangle, well, actually no, just notice that this blue line and this red lines are parallel to each other. Well, you could see that this angle is also alpha. Okay, and the length of this line is actually also a, and this over here, of course, is b. So then the first thing that we can notice is that this alpha plus phi prime is 180 degrees, right? So that's why this phi prime is equals to pi minus 2 alpha, right? So for one, and the other thing is that if you look at this triangle, right? So in the sphere, you see that sine alpha is given by b divided by a. Okay. And this sine alpha, using this one, right? So you also conclude that this sine alpha, in fact, is just cosine of phi prime divided by 2. Okay. And therefore, the relation between b and the scattering angle phi prime is obtained already. Is that b equals a cosine phi prime divided by 2. Okay. So this is a key result. And then the next is just to take the derivative, right? So this db d phi prime is given by minus a divided by 2 sine phi prime divided by 2. And well, I have a minus sign here again, but as I said, right, so just the absolute value is relevant. Okay, so at the end, so this d sigma d omega, this b divided by sine phi prime times a divided by 2 times sine phi prime divided by 2, where I have dropped the minus sign. Okay. And this b is also a cosine phi prime divided by 2, right? So let me actually write it over here. So then that's what we have, right? So you can see that I have this sine cosine in the numerator and this sine in the denominator. Okay. So and however, luckily, right? So this sine times cosine times 2 would be equal to sine. So that is, I'm going to just use this sine 2x equals 2 cosine x sine x, right? So if I use this formula to simplify the whole thing, then you'll find that this is just a squared divided by 4. Okay. So it is so simple that this is just a constant over here. And if you go ahead and find the total scattering cross-section, okay, so that's why this example is actually quite illustrative, as you see the final result here in a minute. So the total scattering cross-section is 2 pi, right? So integral of the differential cross-section. So just this. Okay, so if you actually do the integral, you will find that this is pi a squared. So what is pi a squared? Pi a squared is exactly the cross-sectional area of this sphere itself. Right, so in this case, scattering cross-section is exactly equals the cross-sectional area of this sphere itself. And physically, that makes perfect sense, right? So because, as I said, right, so if you try to, well, as I said, if you try to have a shower of particles, right, so going in, so like this. So only the part of the beam in a particular region will be scattered, which is just this part of the beam will be scattered. Right. So you can increase your region of the beam, right, indefinitely, right? So but all these won't be scattered because they have no chance, right? So they hit the sphere. So that's why the scattering cross-section is exactly equals to the cross-sectional area of this sphere itself. Okay. Right, so if you have that intuition, right, so you should be able to obtain this result. Okay, so even without this calculation over here. Okay, so this is the end of this part of the chapter, and also this is the last part of the chapter 3. Right, so as I said, right, so this scattering problem, okay, will not appear in your exam in this course. Okay, so although you may still get a homework problem. Okay, so but later, okay, in the future, okay, so when you learn maybe in your quantum mechanics class, okay, so you may see a quantum version, right, so of this scattering of particle problem, because this is an important problem in in atomic physics, okay, nuclear physics, particle physics. Okay. So let's move on to the next chapter, and I would say that would be a very interesting chapter, which is on the so-called coupled harmonic oscillator. Okay. So, of course, harmonic oscillators. So before talking about coupled harmonic oscillators, so let's do a quick review on harmonic oscillators. So that is the full name is simple harmonic oscillators, right? So it's just what you have learned before, right? So I'm sure that you have learned about this mass spring system and this simple pendulum, right? So in this case, you have this mass attached to a spring, and then the other end of the spring attached to a fixed point. And if you just stretch the spring, right, so such that the mass is displaced to one side, so and what it does afterwards is will oscillate like this, right? And then the fact that it also, well, the reason why it oscillates like this is because there's a restoring force acting on this mass, right? So by the spring, right? So and that restoring force is given by minus kx. Right? So then this is the equation of motion you get. I'm sure that you're familiar with, right? So and the second typical example that you have seen is this simple pendulum, right? So the whole system is under uniform gravity downward, right? So mg, right? And this particle over here will swing, but due to the combined effect of this tension and also the gravitational force, right? So this particle here will swing left and right like this, right? So and that angular displacement as a function of time, right? So it's governed by this equation of motion. Okay. So mathematically, right? So you know the solutions, right? So of this or this equation, right? So they are the sine cosine function, right? So because as we have learned in the last semester, right? So this is d square x dt square plus k divided by m x equals 0, right? So and then hope that you still remember how to solve this differential equation, right? So you get this characteristic equation, right? So lambda square plus k divided by m equals 0, right? And then the lambda is equals to plus or minus I times k divided by square root of k divided by m. And that's why the general solution, right, x as a function of time, is given by a, which is a constant, cosine square root of k divided by mt, plus b sine square root of k divided by mt. Right, so that's the general solution. Alternatively, right, so you can also write this as let me put it c1 e to the I plus c2 is e to the I, right? So in this complex notation. Okay, so and one more thing on the side. Okay, so just we want to remind you, and then we'll get into what is coupled oscillator. Okay, so if I have this mass spring system, okay, so this is what we had just now. So what if we have a mass spring system with a constant external force? Okay, so you might have learned about it already, because you might have encountered a problem where you put the mass spring system vertically, right, such that the whole system is under constant gravitational force, right? So this is a problem that I'm sure that you have encountered before, right? So and that this is equivalent to say that I have this mass spring system in the horizontal direction, but I applied a constant external force F0, right? So in one direction. So in this case, so I just want to remind you that even you do that, right? So but the oscillation frequency of the system won't be changed by doing this, by applying this external force, right? So why is that? Right, so because in this case, right, so even though my equation of motion looks different, right, so with this F0 term, however, if you do a variable change, you find that this equation can be written like this, right? So with this variable change, then you realize that so the form of this equation is still exactly the same as the form of this equation over here, right? So that's why the oscillation frequency is still exactly the same. Okay, right. So and the other way to look at it is that, right? So if you still remember what we had last semester, is that this equation can be written as d square x dt square plus this equals f0 divided by m, right? And mathematically, how do you solve this equation? Well, if you don't want to do this variable change, is that you know that the general solution of this is equals to a sum of two parts, right? It's the complementary solution and the particular solution, right? So then the complementary solution of this equation, right, is exactly the general solution of this equation, right? So that's why you get the same oscillation behavior. And what about the particular solution? Right, so the particular solution will just be a constant, right? So because the right-hand side is just a constant. Okay. Okay, so now let's get to the so-called coupled harmonic oscillator. Okay, so the coupled harmonic oscillators really means that I have two or even more more harmonic oscillators being connected to each other. Okay, so just imagine that I add another spring to the right-hand side and then attach it to another mass. And then you can keep doing that. And so on. Okay, so of course you could imagine that if I do more and more, the math will be more complicated, but that's the idea. Okay. So and the idea of coupled harmonic oscillators, okay, so you will find it useful, okay, even when you go to another course like solid state physics, right? So if you think of the solid, right? So basically we have many atoms, so in an array, right? So basically that's the lattice, and then the interaction, okay, so between the adjacent atoms, okay, so in some case where the approximation applied can be modeled as this mass spring system. Okay, so but that's something that you might see in the future. But okay, so here let's start our discussion. So I'm going to start with a very simple case. Okay, so where I do have more than one mass. Okay, so you can see that I have two masses here, but still I just have one spring. Okay, so I guess this might not really be called to be a coupled oscillators, because if I want a coupled oscillators, I should have at least two springs. So in some sense, but let's start with this. Okay, so two masses, one spring. Okay, so now in the top picture here, so everything is in equilibrium. Okay, so the length of the spring is at its natural length, L0. Okay. So and suppose so you just drag it on both sides, right? So you use your left hand to pull the left mass to the left, and then you use your right hand to pull the other mass to the right, right? Just like this. So after you do that, you just release them. Okay, so we want to see the subsequent motions. And what happened is that, of course, now that this spring is clearly stretched, and that's why the mass on the left will move to the right, right? So, and then the mass on the right will move to the left. So now, if they do that, they will, after some time, right? So they will pass through the equilibrium point and then go further, such that now the spring is compressed, right? So now that the spring is compressed, then it want to push this one and this one away, right? So then this mass will try to go back to the left, and this one will go to the right. Okay, so this is, and this whole process repeat over and over again. Okay. So then the question now I want to ask is, what is the frequency of this oscillation? Okay, so I mean, is it different from what we have over here? So this one is square root k divided by m. Okay, what about this one? Okay, so this is the first question I want to encounter here. So then how do we do it? Of course, equation of motion, right? So we need to write down the equation of motion. So the two coordinates that I'm going to use is the x1 and x2. Okay, so be careful here about the sign. Okay, be very careful here about the sign. Okay, is that I am considering everything to the right to be positive. Okay, so that is to say, okay, so you can see that I have this line indicated the equilibrium position. If this mass is moved to the right by some distance x2, okay, so then this one, I will say that the displacement of this mass is positive x2. Okay, so this is positive x2. So, and on the other hand, okay, so let me draw an additional picture here. On the other hand, if the left mass is also moved to the right a little bit by a distance x2, x1, I'm sorry, x1 for the left mass, x2 for the right mass. If it happens this way, I will say that this mass on the left has a positive x1 displacement. Okay, that's what I will set up the convention. Okay, so therefore, now that if I am if this mass is moving to the right, to the left, then the displacement will be negative. Okay, so the displacement will be negative. Okay, so and I will still call this x1. Actually, I will still call the displacement x1. Okay. However, if I'm just asking the distance between this mass and the equilibrium position, then I will call this minus x1. Okay, not x1. Because now that x1 itself, okay, x1 itself is negative. Okay, so then minus x1 is a positive number. Okay, so this distance here is minus x1. Okay, so that's, be careful. So now if I really like stretch the spring like this, then how much the spring is extended? Right, so that would be this part plus this part. Okay, so that's the total distance that it is extended. So that's why that would be x2 plus minus x1. That's why x2 minus x1. Okay, so I give you another situation. Let me give you another scenario. Is that suppose both masses move to right by some amount. So suppose this one is like this, this one is like this. So if that happens, then I will say that this is x1, right? And this is x2. Okay. So that in this case, how much the spring is stretched is also given by x2 minus x1. Okay. So therefore, the way I write it will be able to represent any configuration. Okay. And sometimes the spring is not stretched. It is compressed. Right. So just like this. It may be at some moment, it may be like this. Okay. So if in this case, again, I ask how much this spring is stretched, then you will tell me, no, this spring is not stretched, it is compressed. But okay, that means you are going to give me a negative number. Okay, if I ask you how much is it stretched or how much is it extended, then you give me a negative number. Okay. So, and in this case, this x2 minus x1 would be a negative number, right? So because now x2, if the mass is over here, x2 itself would be a negative number, right? And then x1 is a positive number. So this one is negative. Okay, so this term, sometimes positive, sometimes negative. So now equation of motion, right? So because the only force that we have is the force due to the spring. Okay. So, but we do have two equations of motion because we have two particles. Okay. So equate for the particle on the left. For the particle on the left, the force is this one. And if you look at this picture, right, so the force will be to the right. And that gives this k times x2 minus x1. So, and for the particle on the right, right, so you don't need to think again because you know that this is an action and reaction pair. Right, so that's why particle on the right is minus k x2 minus x1. So this one over here. So these are the two equations of motion that we need to solve, right? So in order to find out the oscillation frequency of the system. So here, let me do one simplification, is that I assume the center of mass of the system is at rest. Okay. So indeed, there are no, I assume that there's no any external force, right? So that means there are only two possibilities. Either the center of mass of the system is at rest, or the center of mass of the system is moving in a constant velocity. Okay. So for simplicity, I pick the first case, that the center of mass is at rest. Okay. And if you do that, then you will tell me that at any time, okay, x2 has to be equal to minus x1, right? So that is, if it go this way by 1 centimeter, this one has to go the other way by 1 centimeter, right? So that's what it means. So then I have this relation between x1 and x2, right? So then I can really substitute it back to my equations, and well, something you know how to solve now, right? So this this equation, right, just have to contain the variable x1, and this equation only contain the variable x2. And from this coefficient here, you tell me that this oscillation frequency is square root of 2k divided by m. Okay, so two remarks here. So first of all, we do have this system of, so this is a system of linear ordinary differential equation. And in fact, in 2051, we did have a part of the chapter that consider this type of equation. So mathematically, we in fact know how to solve it, and I'll go to that next. Right. So, but here we did use one physical assumption to first simplify the problem. Right. So to make it a looks like a non-coupled system. So the second remark here is that, okay, so now here you see that the oscillation frequency is not just square root of k divided by m. Instead, it is square root of 2k divided by m. Okay. Any physical intuition for this? Any physical intuition for this? So then I need to go back to ask you one question. For this system, so the natural length of this spring is L0, right? So do you know that the spring constant depends on L0? Have you learned that? The spring constant actually depends on L0. So to be more precise, the spring constant is inversely proportional to L0. You might have learned this before, but okay, so this is if not, okay, so let me tell you why it is the case. Is that if I have a spring, let's say, let me open a new slide. Okay. So I'm considering two different situations, right? So the first one is that I have a spring that has a natural length of L0. And then I have another case where I have a spring of natural length 2L0. L0 and L0. So I'm going to use this spring to build a harmonic oscillator, and I'm also going to use this spring to build another harmonic oscillator. Right. So that is to say, I'm going to attach a mass, and here also attach a mass right here. So, and let's say I stretch them in the same way. X. Okay. So then now the question I want to ask is, okay, same stretching for both cases, but is the restoring force the same? The answer is no. Okay. So why is that? Because this one from L0 to L0 plus X, okay, so that's why the force is minus Kx. Okay, no problem with this one. Okay. However, look at this one. So I told you that I have a spring of length 2L0. So the other way to think about it is that I have two of this spring, and then I connect them in series, right? So then that would make a spring of 2L0. Right? So now that if you stretch this thing, so what happened is that, so let me use two different colors to indicate the two springs. What happened is that the two springs, okay, so they are identical, share the same stretching, the same amount of stretching, okay, such that the spring on the left becomes L plus X divided by 2. Okay. And the spring on the right is also stretched such that the length is L0 plus X divided by 2. Right. So that totally the stretching is X. That means each spring only share half of the stretching. Right. And because of that, the restoring force will be halved. Right. So in this case, force is just minus K times X divided by 2. And I could equivalently write it as minus K divided by 2 times X. Right. So you double the length of your spring, you make the spring constant half. Okay. So that's the idea why K is inversely proportional to the natural length of your spring. So now I want to go back to here. So does that explain the increase of the oscillation frequency over here? It does, because if I look at this oscillator, right, and if I consider the midpoint of the oscillator, right, so the midpoint of the oscillator, right, so since I told you I'm considering the situation where the no external force and the center of mass is not moving, right? So that means that the midpoint of the oscillator is never moving, right? So that is to say, you could just consider this system, right, as two halves, right? So if you just look at this half, what you see is really it's just a regular simple harmonic oscillator, but with a short spring, right? The length is exactly half of the original length. But similarly, you can just look at, right, so what happened on the left, and you again tell me that, well, the behavior just looks like this is one single simple harmonic oscillator, but the spring length is half. So because of that length is just half, right? So then the K is doubled. That's why this is 2K. So this is okay. If you don't really like or don't really fully understand this picture, that's fine for now. Okay, so but at least you understand how we set up the equation of motion. So this part important. Okay. So next, we will use a more systematic way to deal with this set of equation of motion. Okay, because as I mentioned, right, so last semester we do have learned about the how to deal with this system of the linear equation. Okay, so and it is over here. Okay, actually, okay, I may not have enough time to actually start this part, finish this part, but okay, if that's the case, maybe I'll just have you to look at the same problem once more time. Okay, so and then I'll end this. Okay, so okay, so let me just go to this slide. So I just want to consider the same system, but remind you of how the Lagrangian method works. Okay, so in the chapter 2, right? So we only use the Lagrangian formulations mostly for one particle system, and sometimes we do have two, right? So but here, right? So you'll be seeing that we apply the Lagrangian for multiple particles. Okay, so and this is a 2 particles. So then clearly, right? So the 2 generalized coordinates. So let me go back to this term. The generalized coordinate that we are using will be this x2 and x1, right? So and the Lagrangian, right? So the Lagrangian, it would be the kinetic energy of the first mass, the mass on the left, the kinetic energy of the mass on the right, minus the potential energy of the system. Okay. So the potential energies of the system, of course, is the elastic potential energy, right? And that would be the 1/2 k times extension square. And that's why I have this 1/2 k x2 minus x1 square. Okay. So here, one thing to notice is that no matter whether this is compressed or stretched, as long as the amount is the same, then the amount of potential energy is the same, right? So that's why I don't need to worry about the sign over here, right? So x2 minus x1, positive, negative, doesn't matter. I have this square anyway. Okay. So then you can maybe once again see the convenience of using Lagrangian compared to considering the forces. That here I don't need to worry about the plus or minus sign of the force. Okay, just write down the potential energy, and then once you apply the Lagrange equations, okay, so the correct sign, okay, will come out. Okay, so you see these 2 equations are the same as what we obtained here by considering the forces. Okay. Okay, so this one, then I don't need to solve it again, but it's just the same thing. Okay, I think I will just stop here for today. I'll start with this exercise problem next time. Okay. But today we haven't get to the main point yet. Okay, so it's to really how to solve this kind of coupled equations systematically. Okay, and we'll get there next Monday.